Hi everyone, my name is Rachel Doring, and here are my results and processes for Lab 3 on magnetic dipoles. The main purpose of the lab was to measure the distance dependence on the magnetic field due to a small bar magnet at both on-axis and perpendicular observation locations. A brief summary of the procedure was to first download a magnometer app and to find the location of the chip on the phone as a starting point of measurement. Next, we needed to line up the phone so the X component of the magnometer was as close to zero as possible. This step was necessary to compensate for the Earth's magnetic north. Then, we measured the distance between the magnet and the chip, where the magnetic field was equal to multiple different given values. I chose to conduct the experiment outside as to not have any external electronics or metal interfere with the results. Also, this was a suitable location because the Earth's magnetic field measurement from the magnometer was within 2 microtesla of the real magnetic field value found through an online resource using the latitude and longitude of my location. Some key concepts and principles used throughout the lab were the Biot-Savart law for calculating the magnetic field at different observation locations, along with the magnetic dipole moment mu, the relationship dependence to a bar magnet, and accounting for the Earth's magnetic field by aligning the phone so that the X component of the field was equal to zero. The equations listed will prove to be a crucial part of calculating the magnetic field at different observation locations. Here is a spreadsheet for the data collected during the experiment. Listed in the spreadsheet is the average distance between the magnet and the chip reader for 5 different magnetic field magnitudes at an on-axis location. This data was then put into an ln(b) versus ln(r) line graph. The slope of the graph tells us the end value, which is negative 2.5059. The y-intercept of the graph tells us the value for ln(k). The spreadsheet also lists the data for the off-axis, or perpendicular, observation location. The results from the data conclude that the experimental magnetic field at a location 45 degrees is 2.85 times 10 to the negative 5th, 2.63 e to the negative 5, negative 2.6 e to the negative 6 Tesla. Using the fundamental physics principles discussed earlier, along with the data listed on the graph and spreadsheet, we can solve for the K value and the value for the magnetic dipole moment. The calculated K value came out to be 7.008 times 10 to the negative 7th, which was then used to calculate the value for mu, which came out to be 3.5 amperes times meters squared. Here is my full code that was used to calculate the magnetic field using the Biot-Savart law at 6 different observation locations, 2 of them being on-axis while the other 4 being off-axis, to the dipole at the bar magnet. Here is the computational model of the magnetic field at the 6 observation locations. The vectors in orange represent the on-axis magnetic field, while the cyan arrows represent the 4 perpendicular vectors for the magnetic field. The green arrow represents the magnitude and direction of the magnetic field at an observation location 45 degrees from the bar magnet. The values of each of the vectors are listed on the right. The value of the 45-degree observation location is 8.344 times 10 to the negative 6th, 2.5 times 10 to the negative 5th, 0, with a magnitude of 2.63 times 10 to the negative 5th Tesla, and the vector is juxtaposed with the calculated value at the same location. The results of the experiment would be far less accurate if we did not compensate for the magnetic north, as the Earth's magnetic field would interfere with the magnetic field created by the magnet, thus altering the final results significantly. If we were to stick 2 identical magnets, as used in the experiment, end to end, we can expect that the magnetic field would increase at each observation location due to the superposition principle, while the direction of the magnetic field would remain the same. In conclusion, the on-axis magnetic field points in the same direction as mu, while the perpendicular or off-axis magnetic field points in the opposite direction as mu. And finally, the magnitude of the magnetic field decreases as the distance increases.